So at the moment, we need to finish up eigenvectors and eigenvalues, spectral theory. I guess we won't finish it up today. We will really finish it next week with diagonalization. Today, I mean, we're going to finish sort of the introductory part. I would like to start on diagonalization today, if we could. So some of those questions might appear in the midterm. I know diagonalization appears on the schedule for tomorrow, but since we've been spending a lot more time on class time, it's kind of hard to have a short lecture before the exam. I don't know how much of those lectures, like lectures before the exam, I think oftentimes get forgotten because students are so busy concerning themselves about what's going to actually be on the exam that you kind of forget the lecture. Like you'll watch or listen to the lecture, and then as soon as the exam happens, that's really what you're focused on. And so it's almost like you have to redo that material anyway. So I'd like to at least get to some of diagonalization today, if we can. If not, if you check the schedule for next week, we will finish diagonalization, sort of an important result in terms of spectral theory, eigenvalues, eigenvectors. We will look at maybe some applications of spectral theory, and then starting on Wednesday, we'll talk about orthogonality in the Gram-Schmidt process. That, I think I've said in previous lectures or previous days, it's not too hard. So it's kind of a bit of an easy topic to end with in the last few days before the final coming up. So that way we're not really throwing anything too difficult at you right before the final. Okay, so spectral theory part 2. I think we stopped in the middle of an example yesterday, did we not? Let me pull up my notes from yesterday. So we were working through an example where we had a matrix. Let's see, 5, 10, negative 10, negative 5, 2, 14, 2, negative 4, negative 8, and 6. And we found that our determinant of a minus lambda times I was equal to, we did all the computations yesterday and we ended up with this guy. And of course, we're looking for the eigenvalues, so we set that equal to 0. So we want to set each factor equal to 0. First one's easy, just a linear factor. The second one, we want to look for any factors. So it looks like it's going to be lambda minus 10 quantity squared. And so we get lambda equals 10. So once we have the eigenvalues, we go back and look for the eigenvectors. So if we recall, we're essentially looking for vectors that satisfy this equation. Namely, they're going to be kernels of this a minus lambda times I. So we go ahead and plug in the specific values of lambda that we found. figure out the matrix. So this just means we're going to subtract 5 from the diagonal. And so what are we going to get? We will have 0, minus 10, minus 5, 2, 9, and 2, minus 4, 8, and 1. Since we're in 3 dimensions, we'll write x, y, z for our vector. And that's going to be equal to 0. And so now we've reduced the problem down to a problem of row reduction, or finding a system of linear equations. So what do we want to do? Let's go ahead and make the augmented matrix. There's 0, minus 10, minus 5, 2, 9, 2, minus 4, 8, 1. And we want to solve this. So let's go ahead and put that row first. Let's go ahead and move the top row down to the bottom. And then put this middle row, the bottom row in the middle. And then let's take 2 row 1 plus row 2. The 2 in the leading position, not too bad. I'm just going to go ahead and keep it there for now, just so we don't have to deal with fractions like a 9/2. So we'll get a 0 here, and if I take 2 times row 1, that's going to be 18 and 8. It's going to be 26, not necessarily a nice number. We'll have 5 here. In the bottom row, we can do that in an extra step. Bottom row we can keep as it is. So we've got 2, 9, 2, 26. That is not a nice number. Let's go ahead and factor out of a 5. Factor out a negative 5 from that last row. Now, I think it's going to be easiest to eliminate that 26. We've got 2, 9, 2, 0, 0, 2, 1. And let's go ahead and do minus 13 row 3 plus row 2. So that'll give us a 0 there. We'll have negative 13 and 5, gives us a negative 8 there. And let's see, did I do something wrong? Did we do something wrong? Ah, dang it. I had to have copied the numbers wrong. So we should expect to get a row of zeros somewhere. We knew for a fact that the determinant of this matrix should have been 0, which means the rows are linearly dependent. So, did I copy everything down wrong? We have 5 minus 10, 5, 2, 14, 2, minus 4, 8, 6. And lambda was 5. So it gives us 5, 9, and 1 on the diagonal. There's a minus 4 here. Here we go. Sorry, I missed a minus sign there. 1 minus sign throws everything off. Let's go back and make our corrections. So we needed a minus sign here. And then when we flip those, that 8 should have been negative, and that 26 was our issue. So what should that number be? We have 2 row 1 plus row 2, so that was going to give us a negative 10 here, or a 10 here. Yeah. And that looks a lot better. So it should have been 10, 5. Of course, this one 10, 5. And now, when we factored it out, let's go ahead and just move to the right here. We'll have a 2, 9, 2. We'll have a 2, 1 in both of these rows. And so I can eliminate that last row. So these are good practices. We had a good practice yesterday or the day before. Practice problem solving. So it's kind of good when you can understand where and when you have an error. So remember that when we're solving these eigenvector and eigenvalue problems, after we found the eigenvalues and we're looking for the eigenvectors, we should always end up with a one parameter, at least a one parameter or a possible 2-parameter family of solutions. So meaning at least one row should be zeros when we row reduce. So when I got to here, I realized, uh-oh, something's weird. We made a mistake somewhere because clearly I won't have a row of zeros. So go back. Might have missed a minus sign somewhere. You might have added a couple numbers wrong in your row reductions. So always check those out. And let's see, from here, do we want to do anything? I guess we could do some fractional work, or we could just, we could potentially leave it as it is. I'm trying to think if there's easier ways to get this without complicated fractions. We could always add like -2 times this row plus that one, which would eliminate that 2 there. Let me show you how some of these solutions work. If you want to try to avoid fractions, of course, we could always take, -9/2 row 2 plus this one. We could leave them as they are now and write out the equations as well. Either way, we should get consistent solutions. And then ultimately, of course, what are we looking for? We're looking for just some eigenvector. And again, we're always going to have 1 degree of freedom, at least, in choosing this eigenvector. So let's go ahead and do -2 row 2 plus row 1. See if that makes our lives any easier. Because if we do -2, that'll give us a -4. So we'll have a 2, 5, and then 0. So I know it's not necessarily row echelon form or reduced row echelon form, but it simplifies our equations. The top one says 2x plus 5y equals 0. And then the bottom one says 2y plus z equals 0. So I think, regardless of kind of how we're doing it, we are going to get some fractions here and there. Maybe with a clever enough choice of z, we can find it. So let's see. Do we want to pick a nice choice? So this just says 2y equals -z, or -2y equals z. And so what do we want to pick for our z? Let's pick something like, I don't know, 2 or 4. So if z equals 4, y is equal to -2. And then if y is equal to -2, not going to work. Well, nah, that will work out. So then we'll have 2x plus 5 times -2 equals 0. So x is equal to 5. So I kind of just guessed there. I was kind of realizing these 5 and 2 are co-prime. And of course, we have a factor of 2 here, another factor of 2 here. So I felt like if I made z have 2 factors of 2 in it, namely z equals 4, was my choice, was my thinking behind that choice, and I was hoping it worked out, and turns out it did, because then my y was able to be even since we divided by that factor of 2, and then since y was even, we could solve for a nice integer value of x. Again, not the only solution. We could have row reduced and gotten rid of this 9 and then worked with like 9 halves and whatnot. Not too big of a deal, not too hard of a fraction to work with. So here we have our vector v is 5 minus 2 and 4. And then let's go ahead and work out what's going on with this other eigenvalue. For lambda equal to 10, we want to subtract 10 from our diagonals now. So we'll have a minus 5, minus 10, minus 5. We'll have a 2, 4, 2, minus 4, minus 8, and then 6 minus 10 gives us minus 4. And so we're going to row reduce this guy to look for our vector. Now, nicely enough, these numbers worked out really nice because we can factor out things from each of the rows. First row, let's go ahead and factor out a negative 5. So we'll have 1, 2, 1. Second row, we'll factor out a 2. So we'll also have 1, 2, 1. And then the third row, what are we going to factor out? A negative 4. And what are we going to get? So every row is actually the same. So if every row is the same, what's it going to row reduce to? Just one row, and then the other 2 rows are zeros. So this is a 2-parameter family of solutions. Meaning we can choose our y and z to be anything. So when we want to find our eigenvectors corresponding to our eigenvalue in such a situation, you want to choose I'll call it the YZ pair to be linearly independent. So since we have 2 parameters, we're making 2 choices simultaneously, and we have to do that twice because we are actually going to find 2 different vectors, 2 linearly independent vectors that both have an eigenvalue of 10. So this, I kind of just put a dash in here for the x. The x has to be determined by our choice of y and z. Our y and z, we have some freedom. So here's what we're going to do. Stick with easy numbers. So let me rewrite what we've got there. What you don't want to do for one, you don't want to pick zeros for both, because if I pick y and z are 0, then x is also 0. So we would just get 0, 0, 0. So of course we don't want a 0 eigenvector. But you don't want to do things like 1, 1 and then 2, 2, because that is essentially the same choice, since 2, 2 is just a multiple of 1, 1. So easiest choices are going to be something like y is 0, z is 1. So this will be our choice 1. And our choice 2. Flip it. Y equals 1, z equals 0. We know that, right, if I was just looking at our YZ subspace, that this is essentially maybe the second, our E2 basis element. This is our E1. So I know that as pairings, those are going to be linearly independent. We would then figure out our X. So here X is equal to minus 1. And then here our X is going to be minus 2. And so what are our vectors? What do we call the last one? I think we called the last one V, right? Let's call this guy U. So U is going to be minus 1, 0, 1. And then V is going to be minus 2, 1, 0. So I'll leave it to you guys to check. We did make these linearly independent. Of course, if we made these into columns or even rows in a matrix, it'd be fairly clear that the rank should be 2 of that matrix. Okay, so homework. Just check. Good practice to check your calculations for these. So check that A times V. Sorry, let's call this guy W. I just used V twice, did I not? Yeah, let's call that guy W. So V was our eigenvector for 5. So do that computation and see if you get AV equals 5V. And then likewise, we should have AU equals 10U and AW equals 10W. So I'll leave you guys to do that matrix multiplication on your own. Let's talk about what happened in this problem, because this is our first example of when we actually saw two linearly independent eigenvectors for a given eigenvalue. Try to keep my notes organized there. So let's try to formalize everything a little bit that we've done so far. So for some matrix, square matrix, this determinant of A minus, I'm going to use X times I. So lambdas, we consider our lambdas our eigenvalues. So you can throw in a lambdas there if we set it equal to 0. When we are just in generally talking about this function, if we just throw an x in there, it makes a polynomial. So if you look at the previous equations, instead of those lambdas, of course, we're going to have an x in there. Don't confuse that x necessarily with our specific x coordinate position. But really, essentially, what we're doing is creating this polynomial. This is called the characteristic polynomial. Of A. Of course, the word eigen means characteristic. If you wanted to call it the eigen polynomial, feel free. And then what we found is that solutions, i.e. roots of the polynomial. Let me introduce some extra notation. The book uses this. It doesn't quite define it. Maybe sometimes denote it. our little c of a of x. So instead of writing out the determinant of a minus x times I, also the other thing that you might see is sometimes it's xi minus a. So whether it's multiplied by a negative sign, it doesn't really matter. Even though those polynomials are technically different, their roots are the same, and that's the key thing. So solutions, roots of the characteristic polynomial usually denoted by lambda, are the eigenvalues of A and then so let's add a little bit new things of what we just found. So the multiplicity of an eigenvalue lambda is the multiplicity of the root in the characteristic polynomial. So what did we actually see before we found these eigenvectors and before we looked for the eigenvectors corresponding to lambda equals 10, or even any of the eigenvectors, I guess? We found our polynomials. Let's go back. Let me pull that up again. That was on our first page here. And what did we notice about the polynomial? That the characteristic polynomial, if we had it completely factored, we realized we could have actually factored this part as a perfect square. And so hopefully you remember from pre-calc, the multiplicity of a root is going to be the multiplicity of the factor that defines it, the multiplicity of the linear factor that defines it. So in this case, we found the root 10 from this factor, and the multiplicity is the degree of that factor. And so that is actually what determines the potential number of eigenvectors that correspond to that. So the fact that we had a 2 here, so in some sense, you can kind of think of it like we really had 2 eigenvalues of 10, and corresponding to each of those 10 eigenvalues, we found 2 vectors. So a couple more definitions based off of that. So I don't know if this is a lemma or a proposition in the book. Let's call it a proposition that lets lambda be an eigenvalue sorry, let me do one thing first. I think the easiest way to do this is to first introduce our definition of eigenspace. So let's let, well, lambda be an eigenvalue of a matrix then the eigenspace of lambda is, so we denote the eigenspace of lambda, usually E sub lambda of A. And that's just going to be the span of all vectors corresponding to that eigenvalue. So that's all we wrote. Written in words, written in math. And so if you remember from our introduction yesterday, really what we were looking for was dimensions where that aren't really changed under a linear transformation. That's really at the heart of what eigenvectors and eigenvalues are all about. And so what we found by looking at this as well, we can stretch it, we can flip it, which means these dimensions, these vectors are only going to be affected by a scalar multiple under the action of a given linear transformation. And we were looking at just one-dimensional subspaces. And what we found is that there are actually, in certain cases, 2, potentially 3 or more dimensional subspaces that are invariant under the action of a linear transformation. And not only that, not only are they invariant, but they are all sort of stretched or scaled by the same amount. So this is what we found in this last problem. So for example, let's just rewrite it so I don't have to keep pulling up these pages. Our example in the previous problem our eigenspace corresponding to 10, we had 2 free parameters. So if we have 2 free parameters, we know that the dimension is going to be 2. And our spanning vectors that we chose are going to be -1, 0, 1, and -2, 1, 0. Of course, we could have chose different vectors. I could have chose a different set of y and z, and then a different set of y and z. I could have chose 1, 1. I could have chose -1, 1. There. As long as we make our choices, our pair choices of y, z, linearly independent, I will get 2 linearly independent vectors. And now essentially what this definition and this idea is saying that it actually doesn't matter what choices we make. Of course, as long as we're making independent choices and getting 2 linearly independent vectors, because x is going to be dependent on those choices, well, we are maximally going to have that set of 2. So it's going to be maximally of dimension 2. And moreover, the span is going to be the same. So of course, if I wanted a choice of 1, 1 here, well, what would happen if I just added these two? I would get a 1, 1 here, and then the corresponding x values that would happen would have been the same x values we found from our defining x equation based on that choice of 1, 1. Likewise, if I wanted 1 minus 1, I could just take this guy minus this guy. So this was w and v. And so because we're taking the span of these w and v's, we are getting the entire set of vectors. So any linear combination of v and w will not only be an eigenvector with an eigenvalue of 10, but it will span the entire set of eigenvectors with an eigenvalue of 10. And we see that this space is a 2-dimensional subspace. So there are 2 dimensions worth of values that correspond to the eigenvalue of 10. And our eigenvalue of 5, we just found a one-dimensional space. What was that vector? Five minus 2, 4. So being a one-dimensional space, all of the vectors will be a scalar multiple of that guy. And so the proposition that goes along with this, so again, suppose we pick some eigenvalue. Some matrix. And suppose the multiplicity of lambda is k. Then the dimension of the eigenspace corresponding to lambda is less than or equal to k. So this is a pretty deep result. We are dividing up our subspace, or our domain, our entire domain. We would like to divide up into these characteristic directions and be able to find these characteristic directions that are invariant under a given linear transformation. They are characteristic to the linear transformation. And so what we're seeing then is the scaling factors that correspond to these invariant directions. Well, sometimes there's multiple dimensions that correspond to those scaling factors that are invariant. Or I should say multiple dimensions, a multi-dimensional subspace that is scaled by a specific scaling factor, by a specific eigenvalue of a linear transformation. And nicely enough, those correspond exactly, or not exactly, but almost to the multiplicity of the roots of the characteristic polynomials. We've taken a very geometric, very spatially oriented problem, and we've tied it in with a very algebraic problem, roots of a polynomial. So this is a pretty deep result in mathematics. Unfortunately, we have that less than or equal to sign. It would be amazing if it was equal to, that we could always do this. Unfortunately, it says that the dimension of the eigenspace is always less than or equal to k. So as we kind of saw in some previous examples, so for example, in that with our rotational matrix, if we are not rotating by some multiple of 180 degrees, so if we rotate 45 degrees or 90 degrees, there were no invariant directions, right? And so some of these things can happen where even if we do have one invariant direction and one eigenvalue, let's say with a multiplicity of 2 or 3, sometimes the eigenspace that corresponds to that actually isn't 2 or 3. In this previous example, it was really nice that we have, well, the eigenspace corresponding to 10 is two-dimensional, and the eigenspace corresponding to 5 is one-dimensional. And what was the linear transformation acting on? So our A, well, it was a matrix, but corresponds to a 3 by 3 matrix, meaning a transformation from R3 to R3. And so actually what it tells us, the fact that we found 3 eigenvectors, it tells us that we can actually divide up our space and use these three vectors as a basis. As we've shown, these two are linearly independent. We'll actually see that if that any vector, or excuse me, any eigenvector, our set of eigenvectors that correspond to different eigenvalues are always going to be linearly independent. Meaning, if we wanted a better choice of basis for R3, instead of the standard basis, maybe we want to choose a choice of basis so that all the directions created, or all of the basis elements under the operation, under the action of A, are going to be invariant, meaning our scales, right? Our basis is the way we scale and define our space. And so it kind of gives us a way of choosing a basis, choosing a coordinate grid for our domain, such that the grid isn't going to change. It's only going to stretch and scale under the action of this linear transformation. That is a very nice result when that happens. Unfortunately, it's not always going to happen, as we kind of see in this case. Sometimes, if we have, even with a multiplicity of 2, that eigenvector or that eigenvalue and the eigenspace corresponding to it might not be full enough dimension. So think of this in terms of like our rotation matrix. Sometimes we have it's just a matter of the linear transformation. There are no invariant subspaces, or the number of invariant subspaces or the dimension of the total invariant subspaces isn't going to match the dimension of our domain. So our goal kind of is to try to get as close as possible to that and see how close we can get to that for a given transformation. So let's take a look at a few more examples. So before we go on with more of that, we want to take a look at some of the basics examples, and then this discussion will lead us a little bit into similarity and to diagonalization. But before we do that, let's do a few more examples, because we do want to talk about the kernel, namely 0 eigenvectors. As well as an easy case, and that is going to be for diagonal matrices. So our goal, to find the eigenvectors and eigenvalues of this matrix. We've got quite a bit of computations again to do, so let's go ahead and try to move through those quickly. 2 minus lambda, 2 minus 2, 1, 3 minus lambda. So we subtract off lambda from the diagonals. We then compute the determinant, and it looks like the first column is going to be good enough. I think you could actually expand upon the diagonal as well. I don't think that would make it that much easier. You would kind of have this, all three of those factors all in one term, but you would still have to deal with them in the other factors. So regardless, unfortunately, these problems are a lot of algebra. So let's go ahead and expand upon that first column. So we will have that guy. We will have a -1 times the determinant of 2 minus 2, 1, and 1 minus lambda. And then we will have a plus -1 times r, 2 minus 2, 3 minus lambda, and -1. So the first factor is always the nicest, just because it does give you a product of all of these terms. Of course, that is most of the work too. So plus 1 on that one. And we're going to have a minus. I'm going to have 2 minus 2 lambda. I'm just going to go ahead and multiply those, and then plus 2. And then minus. Here we've got minus 2 plus, let's do 6 minus 2 lambda. So the minus from the determinant will kill that guy, that negative, and then we'll just have 2 times that. And so 6 minus 2 lambda. And now we gotta multiply everything out. So let's see, we'll have a lambda squared minus lambda minus 3 lambda, and then plus 3 plus 1 will give us a plus 4. Let's go ahead and distribute this minus sign, so that'll give us a positive 2 lambda. And then I've got 2 and 2 with a minus will give us that negative 4. And then what's going on here? So that if we minus 2 and 6 will give us negative 4, negative 2 lambda, and then that negative will give us positive 2 lambda and positive 4. Or let me see, no. Positive 4 times that negative gives us a negative 4. Did I do that right? Double check. Let's check the minus signs. We'll have minus 2 and 6 is positive 4. Minus 2 times a negative, negative 4. And then here I've got a positive 4 again. Minus 2 times a negative. There we get 3. 1 is 4. Lambda squared. Minus 3 and plus 1 lambda. Okay. So far, I think we're good on that step. And then what's going to happen when we distribute? So we'll have a negative lambda cubed. We will have minus plus 4 lambda squared, and then minus 4 lambda plus 2 lambda squared, minus 8 lambda plus 8 plus 4 lambda minus 8 from those two. Simplifying, minus lambda cubed. How many lambda squareds do we have? 4 and 2 is going to give me 6 lambda squared. And then how many lambdas do we have? I think those should cancel, or no? We have minus 8, minus 4, and plus 4. It looks like a minus 8 lambda. And then we have plus 8, minus 8. Nicely enough, those cancel. And then we want to set that guy equal to 0. Leading coefficient is negative. So this just, again, kind of comes down to whether you want to do lambda or subtract lambda from the diagonals. If we did lambda I minus a, you would have lambda minus, you would essentially have to multiply all of a by a negative. So flip all the signs on a, and then add a lambda on the diagonal. So this way I think it's a little less work to get started. It is unfortunate because you have a negative lambda on each term. So you do often end up with a negative leading coefficient, but that's not too bad. You just flip all the signs since we're setting it equal to 0. And then now, nicely enough, it's a cubic. And again, cubics are hard to solve, hard to find roots for. So we can factor out a lambda. We'll have lambda squared minus 6x, 6 lambda, plus 8. And so our complete factorization, lambda times lambda minus 4 and lambda minus 2. So what does this tell us? It tells us that our eigenvalues are 0, 2, and 4. Meaning that if we have an eigenvalue of 0, essentially all that's telling us is that the matrix itself is not 1-to-1. It's not injective, meaning it has a non-trivial kernel, that there are vectors, non-zero vectors, that when let's call that vector x, so that ax is equal to 0. So it's going to send certain vectors to 0. So this is another way of checking injectivity, or at least if we're trying to find eigenvalues, injectivity in the kernel of that matrix automatically is determined by the eigenvectors in eigenspace. If it has a non-zero kernel, we should always find an eigenvalue of 0. And so now we've had previous questions finding the bases for the kernel. That essentially boils down to the process we've been doing for eigenvalues. And in some sense, this process of finding eigenvalues is the same as our process of finding our bases for the kernel of a given matrix. Now, of course, what's going to happen if lambda is equal to 0? Well, I'm just subtracting 0 from the diagonal, which means we are going to have the same matrix and since we are subtracting 0, right, nothing happens, nothing changes. And then when we try to solve the homogeneous system of equations that arises, well, we are literally looking for where the matrix sends a vector to 0. So our row reductions follow. It should be pretty easy about the first and the third lines, if we can kind of see what's going on there. So if we take 1/2, oh no, is that minus sign off? Maybe not. Maybe I'm a little confused. Nope, maybe not as simple as that. If those two were opposite sign, it would be as easy as adding them. Okay, so let's actually go through the row operations. I'm going to actually put this guy as, do we want this as row 1 or row 2? Might be easier as row 2. Let's go ahead and put 1, 3, minus 1 first. Let's put 1, minus 1, minus 1. So I'll multiply this third row by a negative, and then I'll put 2, 2, negative 2 at the bottom. And we want to solve this guy. So if we do row 1 and negative row 1 plus row 2, we will have a 0 here. And then negative row 1 plus row 2, that gives us negative 4, and then a 0 here. And then what do we want? Negative 2 row 1 plus row 3 will give us a 0 there. Negative 6, negative 4, negative 2 will give us a positive 2 and give us a 0 there. And then there's our dependence. We've got 1, 3, negative 1, 0, 1, 0, and 0, 0, 0. So subtract rows 2 and 3, pull out the 4 on row 2. And now, nicely enough, we can eliminate that 3. So minus 3 row 2 plus row 1. So what is our solution? Our z can be anything. Our y actually has to equal 0. And then it says x minus z equals 0. So x equals z. So what's a good choice? Let's say 1, 0, 1. So choose 1 for z, forces x to be 1. We will get 1, 0, 1. Again, check that. So have A act on vector u, see if it sends it to 0. Let's go ahead and check the other two real quick. Lambda equals 2. If we subtract 2 from the diagonal, we will have 0, 2, minus 2, 1, 1, minus 1, and minus 1, 1, minus 1. So let's see, going through our row operations again. I'm going to take row 1 and move it down to row 2, and then factor out that 2 as well. Let's go ahead and move row 2 up to row 1, and then we'll keep row 3 as it is. So we flip those two, and 1/2 row 2. So far, we've got 1, 1, minus 1, 0, 1, minus 1. And then we've got row 1 plus row 3 will give us a 0, 2, negative 2. And then, of course, if we add or subtract 2 row 2 with row 3, we'll eliminate our row 3. Then let's go ahead and get rid of some of these ones. Let's go ahead and do minus row 2 plus row 1. So we will have 1, 0, minus row 2. It gives us a 0. That's not right. Did I do something wrong? Anyone see an algebraic mistake somewhere? Actually, no. Maybe it is right. Sorry. A little weird, but confused myself there for a second. What's going on with this guy? Almost thought it was wrong, and why is that? Because these two equations, the top 2 rows says x equals 0, y equals 0. And what we don't want, we shouldn't get 0, 0, 0. If you get 0, 0, 0, you've done something wrong. We should find a non-trivial eigenvector, meaning non-zero. And our z can be anything. Meaning, we'll probably want to choose z non-zero. So our eigenvector of 0, 0, 1 should work for that. And real quick, let's go ahead and do the last one. Our other eigenvalue was 4. And so what is our matrix now? We'll have minus 2, 2, minus 2, 1, minus 1, minus 1, and minus 1, 1, minus 3. Doing our row operations again. Let's go ahead and flip those 2 rows. Then we're going to do 2 row 1 plus row 2. So we'll have a 0 here, a 0 here, and 0 here. Yeah, nice. And then what do we want? Row 1 plus row 3. Will give us 0, 0, minus 2. So all in all, we could take 1/2 row 3 plus this guy, plus row 1 to eliminate that coordinate. Let's go ahead and flip those two rows and keep that as a 1. So we'll factor out a -2. And then keep our 0 rows at the bottom. And now what does this tell us? This tells us that z has to be 0 from this coordinate. And then x plus y, x minus y equals 0. So x equals y. So our last eigenvector, let's choose 1, 1, 0. So homework. Go through these calculations. You've seen me do it. Go through them pretty quickly. Good practice to check all your arithmetic. So we want to check that AU is equal to 0, that AV is 2 times V, and AW equals 4 times W. Moreover, this guy is going to be the kernel of U, or kernel of A. So that's the eigenspace corresponding to 0 of A, which we've shown should be the span of our U. It was 1, 0, 1. The eigenspace corresponding to 2 is the span of, let's see, that vector we chose as 0, 0, 1. And then the eigenspace corresponding to 4 was the span of 1, 1, 0. So things we can conclude about this guy, even after doing all these work, some more maybe abstract things, some types of things to think about in terms of maybe true false statements. So one, namely this sort of first bullet, that the eigenspace corresponding to 0 of A is the same as the kernel. And moreover, if the dimension of that space is non-zero, i.e. it's at least 1, the dimension of our 0 eigenspace is greater than or equal to 1, then A is not injective. The other thing we can conclude is that since the dimension of the domain, I guess, dimension of R3 is equal to 3, this is our domain, is 3, and the dimension of our other eigenspaces of E2 plus the dimension of E4 equals 2, then we also know by the rank and nullity theorem that the dimension of the image of A has to be 2. So we know that this is, again, kind of a nice result like our last example, right? Our ideal situation is when we have matrices that we can sort of find a basis for our domain, R3, where each of the basis elements is an eigenvector, We can't always do it, but this is another close call where even though one of the basis elements we chose as an element of the kernel, which technically counts as an eigenvector, but because that whole dimension is being collapsed now to 0, we know that at least because the other two eigenvectors have non-zero eigenvalues, that those dimensions won't be killed off. And so we know that the span of the image space will actually be the span of those two vectors. Since each of these two vectors, the subspaces they define are invariant under the operation of A, right? If I hit A times this guy or A acting on this vector, we'll just get a scalar multiple of that same vector. So we're going to get that same subspace. And so the subspace spanned by those two vectors, even though they're stretching in two different directions and stretching by different amounts, the overall subspace that they span will be invariant under the action of A. And moreover, that will be the entire image of A, since the other dimension is killed off. Any questions on that guy? Okay, let's keep going because I do want to get through as much as possible today. And so far, nothing terribly new, at least procedural wise. We've had to chug through a lot of these computations. I hope that some of these bigger picture ideas are starting to make sense. Again, it's going to be kind of hard to draw, but you can kind of imagine here, since we have 0, 0, 1, that is our vertical subspace, what's going to happen under the image of A. It's going to simply stretch that subspace. So the 0, 0, 1 is going to be scaled by a factor of 2. So our A of E3 is what that vector is. It's just going to be stretched up by a factor of 2. The other vectors we have for our eigenspaces, 1, 1, 0 is going to be our vector xy. So this is our vector, what do we call that? I think we call that v, yeah? That's going to be stretched by a factor of 4. So it's still going to go in the same direction. So this is going to be A of V here. And then the third direction, we had 1, 0, 1. So this is in the XZ plane. So our third vector here, that one we called U. So in the XZ plane there. And what's going to happen with that dimension? It's actually just going to be killed off. So it's going to 0. So we can kind of tell that the image of all of R3, so if this is our domain here, it's going to be mapped to just this diagonal plane. So along the direction in y equals x and then spanned vertically. There's going to be this 3-dimensional or 2-dimensional plane, and that subspace will be the image of A. So it's much easier to see these kind of results with our spectrum, with our eigenvalues of a transformation. So let's do one easy example. Let's say we've got A is equal to 1, 2, 4, 0, 4, 7, and 0, 0, 6. What is nice about triangular matrices? We were just talking about determinants earlier this week, and we saw all that calculating the determinant of a diagonal matrix real easy, right? It's just the product of the diagonals. And so if we want to find the eigenvalues, what's going to happen? When we find our characteristic polynomial, well, since we're only subtracting off lambdas from the diagonals, we aren't changing the structure of the matrix. It's still a triangular matrix. Meaning, so I should have made these just straight lines, I guess, if we're trying to compute our determinant. When we compute the determinant of A minus lambda I, it's just going to equal 1 minus lambda, 4 minus lambda, times 6 minus lambda. And then we're going to set that equal to 0. What are we going to find? We find all the roots very easily. So, proposition for a triangular matrix whether upper or lower triangular will work just the same by the same principles, right? When we're expanding the determinant, if I expand upon that row with a lot of zeros, it's going to make things real easy for that determinant. So for a triangular matrix, either upper or lower, the entries on the diagonal are the eigenvalues. And I'll leave it up to you guys to actually find the eigenvectors corresponding to these guys. So I will say that anytime you find an eigenvalue that's not a complex number, you will be able to find an eigenvector corresponding to it. So the dimension of that can always change. And so we will know that from this, if we find an eigenvector for each of these three, well, we'll have a three eigenvectors corresponding to A. And moreover, we're going to be then we can choose those as a basis for our domain. And it gives us a much clearer picture of how our domain transforms under the action of A. So let me pause real quick. Let's take a quick break. So let's try to build upon this a little bit in the last 15 minutes of class or so. So from the previous examples, we kind of saw geometrically these eigenvalues and eigenvectors they're really nice. They're a nice way of describing and forming a basis for our domain, and then help us understand what's happening to our domain under the image of a linear transformation. However, computing them, not necessarily so nice, especially once we get into these determinants and finding the characteristic polynomial. Some of these calculations have been quite lengthy, and they've taken us quite a bit of time to get through these. But in this last example, well, we saw diagonal matrices. Those are pretty nice because those are really easy to compute with determinants and then make it really easy to determine the eigenvalues. So just as we kind of saw in our previous section with determinants, we like to use row operations to simplify our matrices. Our row operations have been very fundamental, not only in solving systems of linear equations and reducing our systems of linear equations down to much simpler systems of linear equations, but we can also keep track of these row operations because the determinants of our elementary matrices are very simple. It's either going to be 1 minus 1 or some single scalar multiple that's easy to compute. And so we can also use row operations to help us compute determinants much more easily. And so we want to be able to incorporate those principles now into this process of finding eigenvectors and eigenvalues. So our goal / question is, can we use our principles of row operations, and I'm going to put row / column operations, because now these, I've mentioned this all semester, we haven't exactly worked with column operations, but they're going to start to play a role now in this section. To, let's say, transform a given matrix into, let's see, let's see, transform a given matrix into, well, we'll say into a triangular matrix. Lowercase a there. A triangular matrix, or at least as close as we can get. To help us compute eigenvalues. So that's our big question and our big goal. We want to be able to do this. And so the question is, well, if we want to be able to do this, how? And so at least in terms of answering that, how do we do that? We need to make a big note. So note, any transformations that we apply shouldn't, I should say can't, change the eigenvalues. And so this gives us an extra problem. In systems of linear equations, we were able to show that row operations do not change our solution to a system of linear equations. Turns out column operations don't change your solution set. So by performing these row and column operations, not only are we getting simpler equations, but since we have the same solutions, it helps us arrive at the same solutions every step we take. But we're dealing with a little bit more complicated objects now. We're dealing with a little bit more intrinsic information in regards to these linear transformations, in regards to these matrices. So it's not just a general solution where with a general solution of systems of equations, we have a little bit of freedom, as we've kind of seen, of our choice of manipulating and operating around these systems of equations to get equivalent systems of equations. It's really how we derived and how we arrived at these row operations. But now we're dealing with just a matrix structure in and of itself, and these intrinsic characteristic vectors and characteristic values associated with it. So we've got to be very careful about what types of transformations we apply. We still want to get something that looks like a triangular matrix if we can, but we don't want to mess anything up. So a problem is that for an elementary matrix, E, so it doesn't matter what type, 1, 2, or 3, that EA has different eigenvalues than just A. In general. There might be some fluke cases where sometimes they're the same, but if I just apply a transformation to A and transform it into a different matrix, we're really getting a different transformation. So it's going to mess up the eigenvalues. And so how do we resolve this? So the fix comes from, this is an action called conjugation. Which corresponds to what we call similar matrices. So let's define some things. So definition. So let A be an m by n matrix. And let's take P, also an m by n matrix. With invertibility. So P is an invertible n by n matrix. Then A conjugated by P is the matrix P inverse AP. So when we say we conjugate, this word conjugate, the book doesn't use. We use it in higher algebraic terms. In abstract algebra, it comes up quite a bit. But it is just the operation of sort of squeezing A in between a matrix and its inverse. And it doesn't matter. We could write it PA. We could put the inverse over here. As long as one of the P's is inverted, the other P is not. It doesn't really matter how you notate it. They're logically equivalent. So moreover, if A and B are two matrices such that B is a conjugated matrix of A, then we say A is similar to B, and we write A is similar to B, where similar is just a squiggle line. Some other definitions. An important concept is the trace. So given a matrix A, coefficients Aij, the trace of A is just the sum of the diagonal elements. So before we end, let's write down some big theorem, big lemmas. that sort of link all of this together. So information about the trace. The trace is additive the trace is linear, so it also pulls out scalars. And the trace, it's not multiplicative. However, it is equivalent even if matrices are non-commutative. The trace of A times B is equal to the trace of B times A. And so we can arrive at this last one. This simply as a result of matrix multiplication and how the diagonals entries are obtained from matrix multiplication. And then our theorem is that, we'll say if A is similar to B, i.e. B is equal to P inverse AP, similar matrices are going to have the same determinant. They're going to have the same rank. They're going to have the same trace. And moreover, the characteristic polynomials are going to be the same. And if they have the same characteristic polynomials, they have the same eigenvalues. So what's going on with all this? Hopefully, you'll be able to prove number one, or at least understand why number one is true. Determinant of A should be equal to the determinant of B. If I take a determinant of both sides of this equation, determinant is multiplicative. And I know that the determinant of an inverse of a matrix is 1 divided by the determinant of the matrix. So spell that out in terms of the multiplicative nature. And you should arrive at determinant of A is determinant of B. If the determinants are the same, then the ranks are going to be the same. Well, I guess you'd have to do a little bit of work showing that. Showing why the number, especially if they're not all linearly independent in terms of the rows, of why that is going to be invariant. Hopefully you should understand that since P is invertible, it is an isomorphism, so it's not going to change the rank of the matrix or any space that it acts on. Why is the trace invariant? So the trace is like an intrinsic algebraic property, whereas determinant is kind of like an intrinsic geometric property. It measures our intrinsic volume. The trace, in some sense, gives us an algebraic invariant on our matrices, since we can. The trace itself is an operation that is a linear operation. So it's like our matrices represent linear operations on vectors. The trace is a linear operation on matrices. So it's going to play well with addition and scalar multiplication. And moreover, it sort of ignores the non-commutative nature of our algebraic structure, of our matrix multiplication. So it gives us an important algebraic tool. Why is the trace invariant? So I cannot sort of distribute the trace over multiplication. It's not a multiplicative operation, but because of this third property, it says that I can rearrange the multiplication, even though if the multiplication is non-commutative, the trace is going to ignore that non-commutative nature. So if I take the trace of both sides and then maybe just switch A and P inverse, it'll be trace of B is equal to trace of P inverse AP, which should be in the trace of A P inverse P, which will give us the trace of A. So the last two are a little bit harder to work out, especially in terms of the determinants. But hopefully you can kind of gather it's kind of similar to what's going on with this first bullet. Of course, we would have to subtract off our lambda from both of those and then take the determinant. So there might be a little bit of work to do, especially in regards to these inverted matrices and conjugation that's going on. But computationally, or I guess we could say philosophically, it's kind of at the same heart of what's going on here. Because we're conjugating, because P is invertible, and because we are conjugating, we have a P inverse on one side and a P on the other side, the overall determinant isn't going to change. And so the determinant, the characteristic polynomials aren't going to change either under the action of conjugation. And since those are the same, we will have the same eigenvalues. So we'll get to more of this maybe a little bit tomorrow if we start with a brief lecture before the exam. Otherwise, we'll continue with this on Monday. And this is now going to be our tool. So why we can't row reduce, we can't just straight up multiply a given matrix on the left and do row operations, because that will change the eigenvalues. We can maybe perform row operations on the left and then the inverse row operations, which will correspond to column operations, acting on the right. We can use that process to now simplify our given matrices and help us in our goal to look for eigenvectors and eigenvalues. Any questions?